In this video, we are going to make a register file for our processor. This is the register file data path. We have total of 8-bit registers in the register file. The register file is capable of reading 2 registers and writing 1 registers at the same time every cycle. We have 2 8-to-1 multiplexers. These are used to read 2 different registers at the same time. For this, we set a 3-bit read address A or read address B to read the operands. For writing to any register, we need to follow 3 steps. The first step is to set the destination register on write ADDR pins. Then we set data in pins with new values to be written to a register. And finally, we set the write enable to 1 for just 1 single clock cycle. Data in is connected to all registers, but only 1 register gets updated with the new value. This register is selected by the decoder. 3 to 8 decoder is used for selecting destination register for write. All the components shown in the diagram are designed in previous videos. We designed decoder in a previous video, 8-bit register in 2 previous videos. 8-to-1 multiplexer comes from our standard library that you can download from the link in the description. Let's start designing the circuit in LogicWorks. Important note here is we have to decide about our register numbers at this step. So here I'm connecting input 7 of the multiplexer to the register at the bottom. So this register is my register 7. So I have to make sure that decoder is getting D7 connected to the register at the bottom. So let's confirm that. I'm going to flip this circuit vertically, so D7 is at the bottom. So D7, both at the write from decoder and at the read at the multiplexer, is at line number 7. All the registers have a common clock, common data in, but the write enable signal for every one of the registers is different, and it's connected from decoder and it's driven by the decoder. S2, S0, S2, S1, and S0 signals here are my register write signals. So S2 is the most significant bit, S1 and S0 are the next bits. And the collection of signals here are my write address signals. So what I have here right now, I have the circuit complete for 1 write. So I can write 1 register and I can do 1 read. Let's verify the circuit is working with 1 read and 1 write. And if the circuit was working as expected, we can extend that and add another multiplexer and complete the register file with 2 read ports and 1 write. So I'm going to get the read ports of multiplexer ready as well. So S2, S1, and S0. S2 is the most significant. Let's attach drivers to start testing this circuit. What I need one single clock driver for driving the registers. And I need several binary switches. So I need a binary switch for write address. I open up a space for second and third binary switch. And we also need one binary switch for write enable signal down here. Okay, these are the signals for writing to a register. Let's also attach binary switches to control signal for multiplexer so we can read appropriate register. All right, let's enable simulation show values and start the simulation. The way that we test this circuit is by selecting a register and assigning a value to this register. Then after that, we confirm that we can read this value over the multiplexer. Let's write following values to two of the registers. So to register S register 0, we want to write the value of FA, and to register 6, we want to write the value of B8. So let's start with that. We follow the 3-step shown on the right side for writing a new value to the registers. First thing we do, we set the data in. So we also need to attach the hex keyboard to drive new values. Let's bring hex keyboards. Here's arrow keys to get the hex keyboard connected. All right, let's restart the simulation. Okay, going to set value of FA on the data in, and then I select the write address for register 0, which is 000, and then I set the write enable to 1 for a very short time. Ideally, this should be 1 clock cycle, but as we are making a simulation manually, it doesn't really matter. Just flip the write enable to 1 and then flip it back to 0. So the write should happen with the fast clock cycle we have in here that is guaranteed to be 1 clock cycle time. So rising edge reaches to the registers and write will happen. Now let's verify that this value is written to the register file. FA should be on register 0. So FA has the value of, register 0 has the value of FA. Now let's verify we can read this value over the multiplexer. If we set the multiplexer control to 000, we should see the value of FA. So that confirms that we can write one single value and we can read it. Let's write another value to a different register. This time we write B8 to register 6. We put the value of B6 on data in, and then we set the register ID to 6110. And then we set the write enable to 1 very briefly, and then flip it back to 0. Setting write enable to 1 sends register number 6 signal 1 to the write pin, and that register will pick up the new value of data in. And we quickly do that. So we briefly keep the write enable set to 1, and we let D6 to pick the new value. As you can see, the value of P6 is written to register number 6, and we should be able to read this value on the multiplexer. So if we set S2, S1, S0 to 6, we should be able to read the value of P6. That confirms that one write pin, one read pin are working for the register file. Let's add the second read pin. That is only adding another multiplexer to the circuit. Going to stop the simulation and add the multiplexer. Here we are getting a second branch from register 7. One is connected to multiplexer at the bottom. One is connected to the multiplexer at the top. Same for register 6, 5, 4, 3, 2, 1, and 0. Just make sure you keep the order. So if you are considering register at the top, register 0, that should be connected to line 0 of both multiplexers. Multiplexers are identical, and they just used for reading, being able to read 2 operands at the same time. So there is no difference between multiplexers. Let's connect the binary switches and drivers to the multiplexer so we can test the multiplexer at the bottom too. Going to start the simulation again. Let's start the simulation. Let's go with the right values that we are testing. Value of FA written to register number 000. So register 00 is set on the address, value is set on data in. Briefly write enable and set it back to 0. Okay. Now we should see the value of FA on register number 0. Let's verify that. Let's set the value of both multiplexers to 0 and see if we can read the value of FA. Let's just stop and start the simulation again. FA for data in, select signal to 0, write enable set to 1, and then resetting that back to 0. Let's verify now. Okay, FA is now written to register 0, and we should be able to read that on both registers. So 000 is written to FA, 000 is written to register number 0, and it's on the output of the multiplexer. Let's also write B8 to register R6. Register destination is set here, 6, value B8 is set on the data in pins. Let's set the write enable to 1 briefly and then set it back to 0. Now register number 6 should have the value of B8. That is confirmed. Now we should be able to select this register on any of the multiplexers. Let's select multiplexer at the bottom to 6, 1, 1, 0. And we should be able to read the value of register number 6, and that's what we see in here. So that is sufficient to confirm that the circuit is working as expected. We have 2 multiplexers, we can read 2 registers, we have 1 decoder, we can write 1 register at a time. That is complete. Let's stop the simulation and save this circuit. Next step is to create a symbol from this register file. Save this file as a symbol. Remove all the signal drivers and attach ports. So we need one bus port here, and we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 single bit inputs and 2 bus outputs. Okay, let's attach that. Now it's time to set proper names for every one of the ports. Let's start with the right pins here. Going to save this again. So going back to create a device symbol. Let's attach the circuit. Let's verify the pins again. Write address 220, write enable, clock, read address A 220, read address B 220, data in, output A and output B. That looks good. Let's create a symbol automatically. Name the component register file. Let's have the output ports on the right side. And have the register selects, read address A at the top and read address B at the bottom. Okay, and clock, write address and data in on the left side. Let's generate the symbol. That's how it looks like. It looks good, except we could have output A at the top, so it sits beside read address A, and output B at the bottom, so we sit beside read address B. Okay, we can save this one. Let's save this into our CPU project. Okay, now we have the register file. Let's test the register file. Let's connect a breakout here so we can drive new data here. Move the wire a little so we can see the node here showing the breakout is attached to the bus. Then we attach a clock here, we attach write enable here, and the write controls. The testing is just like the testing we did for initial symbol. We need to write addresses, read addresses, sorry. Read address A, read address B, B2, B1, and B0. Okay. We need binary switches. Okay, let's start verifying the circuit. Start the simulation, set show values to 1. We verify the circuit by setting the R0 register to FA. So let's set R0 register to FA. We have write address 2 at the bottom, most significant, so 0, 0, 0. And we have the address set to 0, data set to FA. Let's enable write briefly and then reset this back to 0. Register A should be written now. Let's also set register R6 to B8. Let's set the data to B8 and set the address register to 6. This is the most significant bit, so we get ID 6 by setting 1, 1, 0 here. Let's enable write and reset this back to 0. Now we should be able to read register 0 on output A and register 6, most significant bit, 1, 1, 0 on output B. That is confirming the circuit is working as expected. If you flip the outputs like 6 on port A, 0 on port B, there should not be any difference. You should still be able to see B8 and F8, this time on different ports. That confirms the circuit is working as expected. You can try all other registers to be sure that every other register is working too. And that is the end of the video.